मेरे तो नाम चेंज कर दे इसका मीट का।
वो डिफॉल्ट ही है।
तो टेस्टिंग थोड़ी, मतलब कुछ और नाम देके करना है ना।
एक्सटेंड।
रुक, हाँ टाइटल रिकॉर्ड में अलग रख देता हूँ मैं, मुझे दिख रहा है। हम्म, उसकी लिंक बस एक बार ग्रुप पे डाल देते हैं। ये लाइव बट अनलिस्टेड पब्लिक कर देता हूँ मैं इसे, हाँ पब्लिश। दिख रहा है कुछ, मतलब नॉर्मल अकाउंट से?
देख रहा हूँ, रुक। हाँ दिख रहा है।
नॉर्मल अकाउंट से दिख रहा है यूट्यूब पे?
हाँ
बट
भेज रहा हूँ,
हाँ
रुक।
ओके कूल। तो स्टार्ट हो रहा है ना अभी?
भेज रहा
हाँ
हूँ।
ओके।
हम्म।
Hello.
I think we can start now.
Yeah. Yeah. So we'll be starting with problem A. So the problem statement says that we have given n integers a1, a2, so on up to an, and we able if we are able to pick an index I such that the opponent will pick an index j, and if ai minus aj is divisible by k, then it is said that like we have lost the match. So the question is if we are able to pick an index I such that there exists no index j such that this is true. So what this basically means is that so they are given k if k divides ai minus aj, then we are lost. So we should be able to pick such an index I. So if k divides ai minus aj, then ai minus aj mod k has to be equal to 0. So ai mod k should be equal to aj mod k. So if in the set, if you are able to find such an index I such that there is no other element in the set which is in the list which is having same modulo with respect to k, then we are done with the problem. So for the given list n, list of n elements, what we can do is like we can go to each I and count for each modulo k how many elements there exist. So like in mod k, there are 0, 1, 2, 3, so on up to k minus 1 slots, and we can count how many i's are in each slot. So we can make an array of count of size k minus 1 of size k, and add the count the frequency of ai's. So we can do c of, so for each I, if we can increment the count of c of ai mod k by 1. If we do that, then if the after this, if you find there exists some ci such that ci equal to 1, this means that there exists there exists an element which a unique element which is I modulo k, and this is like this is the only element. So if you pick this element, there can't exist any other element j which which will be equivalent to this. So if we can if this count is equal to 1, when we can't have another element j such that ai minus aj mod k equal to 0. This can't be possible, because if that is the case, then ai mod k equal to aj mod k. But this is if this is the case, then count can't be equal to 1 because we have two elements present in the set. So this the fact that ci equal to 1 itself proves that whatever the element with this modulo I, I mean, some alpha is exactly the answer for our question. Then once we know that alpha, we can go to the list of elements AI and figure out which element is that. So we can just do mod k and figure out if that is equal to alpha. When that is the case, we can just print out the element AI onto the screen. So that basically solves the problem. And complexity of this would be like basically linear O of n times k, because we are also making the k. I mean, we are just able to do this in like O of n plus k here, because like we are going n times once in the loop, and we are also making an area of size k, and we are going at most two times on the set and one time on this set. So this will be O of n plus k. So that's it. That's it for the problem here.
Okay,
Do you have any
so
question?
I would be presenting the solution for problem B then. So, first of all, if we just have a look at the problem. So, initially we are given an array of all n zeros, And in a move, we can either convert a 0 to a 1 or choose any subarray which has majority number of ones. Um, just a minute. Okay, yeah. Sorry, my screen was not shared earlier. Yeah, I think it's visible now. Okay, yeah. So I was telling that in one operation, you can either convert a 0 to a 1 or choose any subarray which has majority number of ones and the endpoints are also 1 and convert the zeros in this subarray to 1. So we need to tell the minimum number of operations of type 1 that we have to perform so that all elements of the array are 1. And note the important thing in this problem that there was no limit on the sum of n over all the test cases. So approach that is O of n per test case would obviously fail in this problem. So we would see a O of log n approach that would give the correct answer to us. Um, okay, so if I assume if I let's say I took k operations of type 1 and they happened at positions t1, t2, so on up to tk, then first observation is that t1 has to be equal to 1 and tk has to be equal to n. This is because in any move, like if we are converting, so these are the only indices for which operation 1 was performed, and all other positions, all j not equal to ti, got 1 from operation 2. So if t1 was greater than 1, then 1 could have never have got 1. So s1 was initially 0. And if t1 was greater than 1, then s1 could have never been 1, because we always modify within a subarray whose endpoints are 1. So that's why t1 has to be 1 and tk has to be n. Then observation 2 is that ti plus 1 is less than equal to 2 times ti plus 2. This is because, okay, so if I have a position ti plus 1 and this was the position ti, um, so consider let's consider any point in between these two values, call it x. So x was colored in some, x got the value 1 by some iteration of the operation 2. So that means, um, or rather, okay, um, yeah, assume to the contrary. So ti plus 1 was greater than 2 ti plus 2. So if we consider the subarray which converted s of 2 ti plus 2 from 0 to 1, it can have at most ti ones, because ti was the last position which got 1 from observation from operation 1. And in the worst case, all of the 1 to ti prefix would have been converted to 1 before an operation on 2 ti plus 2 was performed. But ti is less than 2 ti plus 2 divided by 2. So this contradicts the condition of operation 2, that you need a majority of ones already in the subarray. Um, So this proves that ti plus 1 is less than 2 ti plus 2. So we knew that t1 was equal to 1 and ti plus 1 was less than equal to 2 ti plus 2. So we need to find the minimum value of k such that tk equal to n is possible. So for that we can just maintain a for loop which at every iteration does cur equal to 2 times cur plus 2, and initially cur was 1. So as soon as the value of cur uh, becomes greater than equal to n, we stop the loop, and the iterations of the loop that we have incurred is the answer for the value k. So since at every time, so the operation cur equal to 2 times cur plus 2 at least doubles the current value of cur. So in at most log n steps, we would achieve the completion of the loop. So the complexity per test case is O of log n, and since n is given to be 1e5 and t is 10 raised to 4, 10 raised to 4 log 1e5 would pass comfortably. So that's it for problem 2.
Yeah, I would be taking problem C. So in problem C, we are given a permutation of I mean we for a permutation P1, P2, so on up to Pn, a permutation of size n. They are defining a score of a permutation P as uh, over all possible subarrays L to R, you take minimum of the permutation from L to R and add them up. So you basically take for all subarrays of this permutation, you compute the minimum value of this thing and add up for all of them. So that is defined as a score of P. Next, we are asked to find all of those uh, permutations with the maximum value of SP. So among all possible permutations, we have some permutations which maximize the value of SP. So let's call them the set of permutations M that maximize the value of SP. Then we are asked to arrange M in lexicographic order and figure out the kth element in this thing. So all the permutations with the maximum value of SP, find, arrange them lexicographically and tell the kth lexicographic one in this set. So the claim in this problem goes that if SP has to be maximized, then the only way this would work is if you have the array arranged like this, like 1, x, 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 so on. Then in the next slot, like imagine all the n slots are currently empty. Then one has two options to go, either to the front or to the end. So if it goes to the front, then we get something like this. We have n minus 1 slots to be filled. Then the second element,
Just a
again,
minute.
2 has two options to go, either to the front or to the end.
The screen is not visible.
The screen is not.
No.
Is it visible now?
Uh, are you writing anything on it?
It's white. It's supposed to be white.
No, it isn't.
I think you have.
No worries. I would present problem C then. Uh, yeah. So okay. Yeah. So my screen
None of the
is.
screens are.
Can you stop sharing once? Yeah. Yeah. We would present problem C from the start. Somebody has asked. Can you please stop sharing now so that I can? Uh, can you stop screen sharing, Sai Kamal?
I'm not sharing the screen.
Okay.
Like, is my screen visible? No, right? Please.
No.
Can you try rejoining?
Yeah, I will try this.
Yeah. I am able to share my screen, so I would present problem C then without any further delay. Yeah, so in problem C, we needed to a value of a permutation was defined as summation I going from 1 to n, summation j going from I plus 1 to n, min of yeah, I'm audible, right?
Yeah, but Kamal's screen is still visible. It's gone now.
Is my screen visible?
It was earlier, it's fixed now. You can continue, Mihir.
Okay. I'm also audible, right?
Yes.
Yeah, okay, fine. So this was the value of S of P, and we needed to maximize S of P. Uh, so, hmm, so the idea is like if we consider only, let's say, n, any subarray which has n as the minimum has to be only the singleton subarray containing n. Then any subarray that has n minus 1 as the minimum needs to have either n minus 1 or n in the subarray and no other element. So the contribution of n minus 1 can be maximized only in the case when n minus 1 n are adjacent in this way or n minus 1 n are adjacent in this way. Next, further, like if we consider the contribution of n, so by count of n, I mean the number of time n appears in this summation. So the number of times this assumes the value n or j for count of j. So that can be only one. Then the other observation is that contribution of n plus contribution of n minus 1, um, just a minute, 3. So I would briefly show why these inequalities would be true. So okay, so let's suppose I had taken the summation till for j terms. Then the claim is basically that this is less than or equal to j choose 2. This is because consider the subsequence of the array of the permutation, which consists of only n, n minus 1, so on up to n minus j plus 1. So if this subsequence was contiguous in the permutation, then all j choose 2 subarrays of the subsequence would have contributed to our answer. But if the subsequence was something like this, n, 1, 2, like if the original permutation was something like this, then we can observe that any subarray that contains n, if this subarray or this subarray, for them the contribution would be coming from 1 or the or any element any element less than n minus j plus 1. But the number of subarrays that are considered now are still j choose 2. So that's why we would get the contribution of n plus n minus 1 plus 1 up to n minus j plus 1 is less than equal to j choose 2. Um, hmm. So now the since our summation was summation I going from 1 to n, I times contribution of I. This is same as summation I going from, or rather j. I took j here. J going from 1 to n, summation I equal to n minus j plus 1 to n, contribution of I. Like you can check that these two things are in fact equal, because contribution of n would come for n times, contribution of n minus 1 would come for n minus 1 times in the RHS, so and so on. And this is less than equal to summation j equal to 1 to n, j choose 2. So we have upper bounded by answer. So for any permutation p, answer is less than j equal to 1 to n, j choose 2. And we can simply observe that for this equality to hold, we just needed that the segment n minus j plus 1 to n, like if we only focus on these numbers, they form a contiguous subsegment of the permutation. So our maximizing permutation, so there is an easy way to categorize the maximizing permutations. They are all those such that for each I from 1 to n, the if we consider only the elements of the permutation from lying in the range I to n, then they form some contiguous segment of the entire permutation. So for example, if I was n minus 5, let's say I was n minus 5, then n, n minus 1, n minus 2, n minus 3, n minus 4. You can see that for all I greater than equal to n minus 5, this condition holds true. So uh, like, or rather, let's take a example of a permutation only. Let's say n was 8. So our maximizing permutation is of this form: 8, 7, 6, 5, 4, 3, 2, 1. So in this permutation, we can observe that 8 was contiguous. Then 8 and 7 were also uh, in the same subsegment. Then 8, 7, 6 were also contiguous. Then 8, 7, 6, 5 was also contiguous. So on, you can check that for each I from 1 to n, the segment I to n was contiguous. Um, so once we have found the characterization of such permutations, we can see that the total number of permutations is basically 2 raised to n minus 1. This is because once you place a number n minus 1 can be either on left side or right side. Similarly, n minus 2 can be on either on the left side of the formed segment or on the right side. So you do this from n minus 1 to 1. So for each step, you had two options. So total ways are 2 raised to n minus 1. Now we are asked to find the kth smallest, lexicographically smallest permutation. So for that, we use the classical technique of uh, checking, like a classical greedy approach of finding the lexicographically smallest permutation. So we check what if we had put 1 at the first position. Then the remaining, so the number of permutations which had 1 in the first position would have been 2 raised to n minus 2. This is because we can simulate the same arrangement for 2 to n, and 1 at the left would have always been valid. Now, what would have been the number of permutations if we had started from 2? So if the leftmost end of the permutation was 2, then the rightmost end had to be 1. 1 could not have occurred anywhere in between these. So this can be proved easily by the visualization of the construction. Similarly, if the permutation had started from 3, then in the end, the number should have appeared in the form 2, 1 in that order. So similarly, if the permutation had started from I, then the numbers I minus 1, I minus 2, so on up to 1 would have appeared in that order. So once you fix the starting position, starting number, you also fix some end segment. So you can recurse on the middle segment to find the k minus, like if the number of total permutations starting with first number less than I were k prime. And if so you can recurse on this smaller block by taking k equal to k minus k prime. So the problem is similar to on the smaller block now, which was for the larger block. So in this way, you can solve the problem in O of n. And um, like the code is a bit long, so I won't go through it in the stream. But once you get the idea, the implementing this is not hard unless you get stuck in some edge cases like me. So yeah, that's all for problem C. Problem D, should I be presenting or because you're
Sai, you
seeing?
can start.
Hello.
Mm,
I have stopped sharing my screen, so you can share now.
Is it showing up?
No, it's a black screen.
Maybe you can just explain your code. Uh, so you can share your screen from laptop and like go through the code, explain the construction through the code itself.
Yeah.
Hmm.
Yeah. So my idea for problem D is that, well, it's open the problem as well. So we are given a tree and we have to assign unique values for one I equal to 1 to 2n to each of the indices of this tree, such that the difference between for any edge that exists in the tree, u, I, 2, v, if there exists an edge in the tree, then the values assigned should be such that the difference, absolute difference in those values should not be a prime number. So that's what was given in the question. And the the nice part of the question is that they gave us the option to go from integers from 1 to 2n. So if we are given integers to go from 1 to 2n, then we essentially have n odd numbers and n even numbers to fill up. So the idea was like, first figure out the do a we will figure out the depth of each of the node in this tree, assuming the tree is rooted at index 1. We'll find the depth of each of the element in the tree, and we'll also find out what is the parent of that element with respect to this rooted tree. The idea is like, if we go in BFS order on this tree and try assigning only the odd numbers to the indices of this tree, we will like, whenever it is possible to assign an odd number to in the BFS order, try and assign the odd number. So if we go this, the claim is that at the end of the day, you will be only left with two slots to be filled. Like, there will be only two slots that remains unfilled after this point. So the way you can prove this is that, assume after uh, like assigning those values, x is the node element that is left, and like we initially have n odd numbers present with us. Then we also have that we are trying to assign each element one by one, and assume at a point we are not able to assign an element to the node in the BFS order such that we are always getting a prime. That could only be possible if, say, an x is a slot that we are not able to fill. Then you see p of x, the parent of x. Let's say the parent of x has a value we assigned to it. What this means is that because v is an odd number and we are still trying to assign only odd numbers because we haven't exhausted all the odd numbers. The only way in which we will not be able to assign is when like, if you are trying to assign a value p to this k to this element, then you need that absolute value of k minus v has to be equal to a prime number. But because k and v are both odd numbers here, the difference should be an even number. So this value should be equal to 2. But that means that there are not many values of k possible. So for a given value of v, the only possible values of k is like v minus 2 and v plus 2. So these are the only possible values of k uh, for which you will not be able to fill the element. But this means like if at the end of the day, after filling all the odd elements out, you would be left with no more than two elements in your odd bucket list. So if you are left with no more than two elements in your, because if you are left with more than two elements, then you will always be able to find an element and assign it so that this condition is not satisfied. Like it won't be equal to two. So this means that at most two elements are left in your odd number bucket. But because there were n odd numbers initially and at most two are left, this means that you have already filled nearly n minus two elements are already filled. After doing this process, n minus two elements are already filled, and then you have two odd numbers, at most two odd numbers left, and then you also have n even numbers left. So for this two slots that are left, you can categorize those two slots as in two categories. Either they could be in a chain form, like an element x followed by an element y. This is how the connection could be with respect to the tree, or it could be like a parent connected to both of them, and p with y. Or it could be like two different parents connected as well, but because we are going in, or it could also be like two different parents exist and they are connected to these slots. So at the end of the day, like you can show that there are like no, there are only three cases in here. In each of those cases, with respect to given constraint, you can show that you will always be able to assign the values. Like the only way this would fail is when you have an odd number x such that x plus even is prime for all even numbers that exist in your lab. So you can show that like this is obviously not true, essentially claiming that you will always be able to fill in any of these configurations. So so basically at this code, like we figure out the depth of each element here. Then with respect to the depth element, we sort in the order to go in BFS. So we make an odd list and even list of elements, and we just append from 1 to n. We just append all the even numbers and odd elements to those lists. We'll erase the first element and assign the first node to be 1, the rooted node a value of 1. Then while there are elements in your list, currently we set mode equal to 1. That means we are filling odd elements in. Then we figure out the element in the BFS order. We pick the top element. Then figure out if the size is 0, switch back to mode 1, which is filling even numbers. Otherwise, take the odd number, take that element, figure out the odd number that is possible, and if odd number is possible, then erase the odd number from the odd number list, pop back the node that you are trying to fill, and assign the answer for that node to be the element that you are trying to assign there. And if you find out that you are not able to assign this case, this will only happen if size of OV OVS is less than equal to 2. This is the only case where this could happen. So if you are hitting this point, then this means that if you are hitting the below point, like either you have assigned the value. This means if you came below this point, this means you haven't assigned the value. If you haven't assigned the value, this means you have already filled out n minus 2 slots from this. So what you do is like you add the remaining odd elements to the even element list, essentially like merging the both odd list and even list. Like take those two elements or what are the number of elements that are left less than equal to 2, add them to the even left, and get back to mode 1. So once you are back in mode 1, you essentially do the same thing. You take the first element out, figure out the parent, and find out the absolute difference is not a prime. So this set of primes you can figure out using, you can just sieve over all the 2 to the power of 5 elements there to figure out the if an element is prime or not. So from that you check if the element is prime. Here, like in this case, you never need to check if the element is prime or not. In the above case, it's enough to see 2 because you're only filling odd numbers in. So the difference is always going to be even numbers. So 2 is the only possible number. But here both odd numbers and even numbers exist in your list now. So the difference could be because like you could be adding it to an even parent or an odd parent. I mean parent with an even value or an odd value. So here you can't be sure. So here you will assign the value. I mean you check over all primes whether it is possible or not. Then if you find the value, just put it in there, pop the element out and assign the value. And the claim is like you can show with this finite number of cases that exists that you will always be able to assign the corresponding values to the only two nodes that are remaining, at most two nodes that are remaining. So once you are done, like so that guarantees that this loop that we have over here will always break out. Once you are done with that, answer of I will contain the corresponding node values for each of those indices side. You print them out onto the screen. So that is my solution to problem B.
Hello, so I'll explain problem E now. So in the problem we have a tree and we put a robot at some node and then we perform some steps. If the step index is odd, if I is odd, then the robot moves towards vertex 1, and if it is even, then it either chooses a random node to be moved to, or we can pay a coin and make it move towards 1. So this gives us intuition to route the tree at vertex 1 and make vertices like this. So at an odd step, it moves towards the parent, or at an even step, we move towards the parent by paying a coin, or choose any random edge and moves toward it if we do not pay the coin. And the process stops when we reach vertex 1, and we have to find expected number of steps to reach vertex 1 if we start at vertex V and have P coins as with us. So we'll make some observations first. First, notice that the constraints are low, not 2e5 or something. And so we could use some order in Q or order n square approach since Q is also up to 2e5. So first we make some observations. First, note that a tree is a bipartite graph. So if we color the vertices red, red and purple, then if we start at a red vertex, then whenever we reach a red vertex, we would be at an odd index step. And whenever we reach a purple vertex, we would be at an even index step. So this means that whenever we reach the same color vertex as the starting vertex, we would move towards the parent. And whenever we reached a different color, we would either have to pay a coin or pick a random edge. So we make a second observation that once we go to this vertex, like once we go to a blue vertex from a red vertex or a like purple vertex from a red vertex, then if we do not pay a coin, then we can either go to the parent or go to the children. If we go to the children, then we would come back again in the next step because that vertex would move to the parent as it would be an odd index step. So this is our tree and we are starting at this vertex. Then in one step we'll go to this vertex. Then we need to count the expected number of steps such that we reach this vertex. After when we reach this, we are guaranteed to reach this in one step. Then we need to count the expected steps to reach its parent. Then we are guaranteed to reach the parent again. So let's see, like when we are at a purple vertex, let's denote its degree by d. We have a uniform probability of going towards any edge. So the expected number of steps to cross this edge is 1 by d. And in 1 by d minus 1 steps, we would not have picked the parent edge. In those steps, we would move to a child and then come back again to the current node. So that would cost us 2 times 1 by d minus 1 extra steps. So for each alternating vertex in the path, we count the additional, we count this additional value that adds to our expected steps, and we pay coin to the ones that have the maximum of these. Like we can sort these purple vertices by this value and choose to pay coin to go through the parent within a single step rather than having to cover these many expected extra steps. So in short, if we do not pay a coin, the answer is depth of vertex plus summation of. So these are the steps that we have to cover to reach the root, and these are the extra steps that we would have to cover without paying any coin. And then if we have some coins, we sort them in reverse order of, we sort the purple vertices in reverse order of this and subtract this extra steps that would have been covered by paying a coin. So my code looks like this. First, I take the input. One second. Yeah, so this is my code. First, I take the graph as the input. Then I run a DFS loop to find the parent of each vertex. Then I do an order queue loop. Take the like here x equals the initial vertex and y is the number of coins that we have. This is for zero indexing. I sort the vector for the purple extra steps taken by the purple vertices, and then I iterate over the parents and add the value that I wrote 2 times degree minus 1. One second. Here D was the probability of picking any edge. So 1 by d is the expected steps to pick a single edge, which is just equal to degree of vertex. So yeah, these extra steps are first added into the answer and pushed into the vector. Then we sort the vector, and while we have coins, we take the maximum element and subtract the extra steps taken from the answer, and then output the answer. Like, note that the answer does not need to be taken modulo because it fits into long range anyways, because this formula cannot exceed long range. So we just take the modulo at the end and output the answer. The final time complexity is order nq because it takes at most order n steps to reach the vertex 1, which is the root. Yeah, that's all.
Yeah, I think we can end the stream now.